This is part 9 of the series Parallel and Perpendicular Lines, and in the last session we ended with discussing the slopes of parallel and perpendicular lines and how to use them. And in this session we're going to start out with a different concept of perpendicular lines, and that is to find the distance between a point and a line. So here we have a line, and we have a point that's not on the line. The distance between a line and a point not on the line is the length of the perpendicular segment from the point to the line. So we have several options. We could have chosen to find the length of this segment or the length of that segment, but the actual distance, the actual shortest distance between a line and a point that's not on the line is the length of the segment perpendicular to the line from the point. So let's just put this into practice and look at a couple of examples. In this problem, we're asked to find the distance from point P to line BC. So here's line BC and point P is up here. We could choose to find the length of segment PB or the length of segment PC, but those are not going to be the distance from point P to line BC. As we just learned, the distance from a line to a point not on the line is the length of the perpendicular segment from the point to the line. And we learned in the last session that a horizontal line and a vertical line are always going to be perpendicular. So this is clearly a horizontal line. This is clearly a vertical line. If you wanted to check that, you could always do the slope of this and the slope of this. But you can clearly see this x-coordinate is 7. This x-coordinate is 7, so these 2 points are over the top of each other. This point's y-coordinate is 2. This point's y-coordinate is 2. So these points are directly side by side of each other. So this is horizontal, this is vertical, therefore this is the perpendicular segment to this line. So that's all we need to do is find the distance from point P to point A. And that's just the distance formula. So let's go ahead and do the distance formula. I'm going to stack point P, 7 and 9, over point A, which is 7 and 2. And we have 7 minus 7, which is 0. 9 minus 2, which is 7. So we've got the distance of the x's, difference of the y's, square them, add them, square root. This is the square root of 49, which is 7. So the distance from point P to point A, or the distance from point P to line BC, is 7 units. Now we could have just counted from here down to here, but you're not always going to get that luxury, as you're going to see in the next problem. In this problem, it's not so terribly obvious which segment represents the perpendicular length. So you can see that this is probably not going to be it, and this is probably not going to be it. We don't want to trust the picture, but I'm going to use the ones that appear to be perpendicular first and start with that assumption. So it looks like these two are perpendicular. So I'm going to find the slope of the line, and then I'm going to find the slope of this, the line going through this segment, and see if these are in fact perpendicular, and if so, that will be the set of points we use to find our distance from point P to line BC. So the slope of line BC then is going to be the difference of the y's, so that's 6 minus -1, over the difference of the x's, 3 minus 10. So 6 minus -1 is 6 plus 1, which is 7. And 3 minus 10 is -7. So this is -1. So that's the slope of BC. And now let's find the slope of PC. So that's the difference of the y's. So it's 5 minus -1. So 5 minus -1 over the difference of the x's, 16 minus 10. So 16 minus 10. That gives us 5 minus negative 1 is 5 plus 1, which is 6. 16 minus 10 is 6, so this is 1. Now we know that two lines are perpendicular if the product of their slopes is negative 1. Well, clearly, negative 1 times 1 is negative 1. So yes, in fact, these two are perpendicular. So line BC is perpendicular to PC. So these are the 2 points we're going to use to find our distance. Let's go ahead and start that. 16, 5. We stack the points. 10, negative 1. This is distance formula. Difference of the x's. 16 minus 10, 6. 5 minus negative 1 is 6. Square, add square root, SAS. So this is the square root of 36 plus 36, which is the square root of 72. We can do our prime factorization. First prime number is 2, so 2 goes into 72 36 times. 2 goes into 36 18 times. And 2 goes into 18 9 times. 2 doesn't go into 9 evenly. Next prime number is 3. 3 goes into 9 3 times. So we have one pair of 2's and one pair of 3's. So this is 2 times 3, and there's still a 2 left inside the radical. So it's square root of 2. So this is 6 square roots of 2, which is the exact value, and that's approximately equal to 8.5 to 1 decimal place. So that's the distance from point P to line BC. All right, now we're going to look at a topic we've covered in a previous series, but we only covered it in one dimension. We just covered it on a number line, and that's called partitioning a directed line segment. Before we were just partitioning a number line, but now we're actually going to be looking at partitioning a directed line segment. Before we can actually partition a directed line segment, it's important to know, of course, what is a directed line segment. A directed line segment is simply a segment that represents or implies movement from one endpoint to another. If we were to say segment AB, and it's a directed line segment, we'd assume we were moving from point A to point B along that line segment. So that's all we're talking about when we say a directed line segment. All right, let's take a look at a specific directed line segment. Here we have directed line segment AB. We're moving from point A to point B. And let's say that we want to partition this line segment. So here's our question. We want to find a point P that partitions directed line segment AB in the ratio 3 to 2. That is, there's going to be some point P along this segment that breaks this into 3 parts on this side of point P and 2 parts after point B as we move from A to B. Now the easiest way to do this is to break this segment into 2 components, a horizontal component and a vertical component. So here is our horizontal and our vertical component. Now the way to partition these things is we're going to find the horizontal component of point P along this horizontal segment, the vertical component of point P along the vertical segment, and find out where those two intersect. Where those two intersect on line segment AB, that is our actual point. So in order to do that, what we want to do is break this horizontal piece into 5 approximately equal segments. So breaking up the horizontal one is easy because this piece is 10 units long. If we go from -2 to 8, that's 10 units. So every 2 units is going to be one of our pieces. So there's one piece here, 2, 3, 4, and the 5th piece. Now breaking up this one, not quite as easy, but we can approximate it. So let's do 1 here, 3, 4, and 5. So 1, 2, 3, 4, and 5. This one's a little big, but it doesn't really matter. It doesn't have to be perfect. Now, we know that there's going to be from point A to point B. So we're going in this direction. So we're moving in this direction. From that direction, there has to be 3 pieces on the A side. So 1, 2, 3. And then there is where our point P should be. So our point P should be somewhere up there. And on the vertical segment, 1, 2, 3. So it should be where approximately where this and this intersect. So point P should be approximately in that region. And we're going to find out exactly where it is. But that's the idea of how we find it. Well, now that's all we have to do is we have to find out how far each one of these is so that we can count. Now this one obviously is easy because we have 10 divided by 5, so the length of this segment is 10 units. And we have 5 pieces we're breaking it into. 10 divided by 5 is 2 units. So each one of these is 2 units. 2, 2, 2, and 2. Now this one's a little bit more difficult. We got to find the length of this segment. Well, this y-coordinate is 12. This y-coordinate is the same as that y-coordinate, which is 3. So this point here is going to be at 8, 3. Because this has the same x-coordinate as this and the same y-coordinate as that. So the distance from here to here is 12 minus 3. 12 minus 3 is 9. So the length of this segment is 9 units long, and we have to break it into 5 separate segments. So 9 divided by 5 is 9/5. So that means this distance is 9/5, 9/5, 9/5. So we have to start counting now. So let's do the x-coordinate first. We're starting at the x-coordinate -2. So we're looking for point P's x-coordinate. And we start at -2, and we're going in this direction, so we're adding these distances. So it's +2, +2, +2. So -2 +2, +2, +2. We're adding 1, 2, 3, because that's where our point P is going to be. So here we have 2, 4, 6, minus 2 is 4. So the x-coordinate of point P is going to be at 4. And let's find the y-coordinate now. So the y-coordinate of P, we're going to start down here because we're going in this direction. That means we're going from bottom to top. So we start at this y-coordinate, which is 3. Plus 9/5 plus 9/5 plus 9/5. So plus 9/5 plus 9/5 plus 9/5. We can simplify this a little bit by saying this is 3 plus 3 times 9/5, which gives us 3 plus 27/5. And if we want to combine these two, we convert this 3 into fifths by multiplying it by 5 over 5. So this gives us 3 times 5 is 15, 5 times 1 is 5. So 3 is 15/5 plus 27/5, and that equals 42/5 or 8.4. So our point P is going to be at 4, 8.4. So that's 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, 8.4. So we got it in almost exactly the right position. And there's our point P. Now, if the directed segment had been B to A, we would have had the same values in these horizontal and vertical directions, but we would have started at this point and subtracted these distances. Started at this point and subtracted. That wraps up this part, and I will talk to you in the next video.